Matrices in linear algebra are used in almost all areas of applied mathematics, often in critical steps of common calculations. One simple example is least squares fitting of a line to data. This shows the fit function used to fit a quadratic polynomial to some data. The critical step in this example is calculation of the coefficients in the quadratic polynomial, which is done within the fit function, which, at least in effect, does that calculation by constructing a special matrix from the data and using a matrix operation called pseudo-inverse to get the coefficients. The dot in that input is the matrix dot product operator. The dot is a special notation for the dot function. The matrix here is represented as a list of lists, which is how general matrices are represented in the Wolfram language. The matrix can be displayed as an array of elements using matrix form. The matrix in this example has 5 rows and 3 columns. Each sublist represents a row in the matrix, and the elements in each sublist are the elements of the matrix. A vector is represented as a list. Matrix form displays a vector, such as the data in this example as a column. With those notations, the input with pseudo-inverse can be written like this, which gives the same coefficients as before. The pseudo-inverse is itself typically computed using other more basic matrix operations, such as singular value decomposition. For example, this shows the fit coefficients computed by applying the singular value decomposition function to the matrix that was constructed earlier from the data. Another very common application of linear algebra is in solving systems of linear equations, which come up in many applications. For example, this graphic illustrates an application where a weight is supported by the 3 legs of a tripod, and the goal is to calculate the weight supported by each leg. A bit of basic physics leads to a set of 3 equations to be solved for the weights W1, W2, and W3. Similar sets of equations arise in electric circuit analysis, where the variables typically represent currents or voltages, or similar equations come up in analyzing manufacturing processes or financial systems, or in many other applications. Regardless of where the equations came from, the equations can be solved using the solve function. Inside the solve function, this solution is computed by turning the calculation into an exercise in linear algebra. This set of equations can be written as a single matrix equation using arrays in which the elements are the coefficients from the equations. The original equations can be recovered from this matrix equation by using thread to get a list of equations rather than an equation between 2 lists. For computing the solution, however, the explicit equations are not needed, since the calculation is done entirely using the arrays of coefficients. A mathematically straightforward way of computing the solution is to multiply each side of the matrix equation by the inverse of the coefficient array, as in this input, which uses the inverse function to compute the solution. A more efficient approach uses the linear solve function, which takes the same coefficient arrays as arguments and returns the same solution. The linear solve function can also be used to construct a special structure based on a linear solve function expression, and that linear solve function expression can then be applied as a function to the vector on the right side of the equation, which again gives the same solution. The linear solve function expression is convenient when calculating the response of the same fixed system to different inputs, such as the response of an electrical circuit to different current or voltage sources. Returning to the equations that were entered at the start of this example, the arrays of coefficients from those equations could be constructed in many different ways, but perhaps the easiest method is to use the built-in function coefficient arrays. The result from the coefficient arrays function uses sparse array expressions. Sparse array expressions can usually be treated just like any other array. Those sparse array expressions can, for example, be used in linear solve to compute the same solutions as before. One detail worth noting is the minus sign in that input, which is a consequence of a sign convention in the coefficient arrays function, which is that the coefficients are based on equations where the right side of each equation is 0, which here has the effect of inserting a minus sign. Applying normal or matrix form to a sparse array expression converts the expression to a dense array, which means an array that is stored in the computer in such a way that every element is specified explicitly. The minus sign in that last vector is again a consequence of the previously mentioned sign convention in the coefficient arrays function. In linear algebra, a sparse array is an array in which most of the elements are 0, and sparse array expressions typically come up as an optimization for working with sparse arrays. This input, for example, uses sparse array to represent a matrix in which all but 2 of the elements are 0. The first argument in sparse array is a list of rules that specifies which elements are non-zero, and the second argument gives the dimensions of the array. Sparse array expressions provide a way to represent sparse arrays without the need to store and manipulate all of those zeros. The first argument in sparse array can also include patterns to specify groups of array elements. For example, this input uses two rules. The first rule uses a pattern to specify values for all of the array elements just below the diagonal, and the second rule gives a value for one other element. An alternative to matrix form is matrix plot, which gives a graphical representation of the matrix. The display for matrix plot uses different colors based on the size of each matrix element. In this example, zeros are shown in white, positive elements are shown in varying shades of light brown or orange, and the one negative element is shown in blue. The details of that display can be controlled using options of matrix plot. Sparse arrays are especially beneficial in working with large arrays. For example, this constructs a 100 by 100 sparse array, so this is an array with 10,000 elements, most of which are 0. Byte count shows that the sparse array uses about 25 times less memory than the dense array. The dense array is generated here by applying normal to the sparse array. Matrix plot is especially useful for visualizing large matrices like this. The display from matrix plot provides a quick way to see which elements in the matrix are 0 and the arrangement of non-zero elements. Another optimization when working with arrays, which typically happens automatically, is a memory optimization that applies to arrays in which all of the elements are machine numbers of the same type. A machine number on this computer uses 8 bytes of memory, but the byte count function shows that the Wolfram Language expression used to represent a machine number uses more than 8 bytes, and a list containing that number uses even more memory. The additional bytes are needed because the elements in the list could be anything, including integers or machine numbers or fractions or high precision numbers or symbolic expressions or anything else. And the additional memory is needed to distinguish bytes that represent machine numbers from bytes that might represent something else, and also to indicate where those elements are stored in the computer. In practical applications, however, it is very common to encounter arrays like this one where all of the elements are machine numbers. For this common special case, the Wolfram language automatically stores only the numbers. For example, this input generates a 1000 by 1000 array of inexact machine numbers, so this is an array with 1,000,000 elements, and byte count shows that this array uses about 8 million bytes of memory, or about 8 bytes per number, which is the optimal way to store this array on this computer, plus a few bytes to indicate that all of the elements are machine numbers and to store things like the dimensions of the array. This optimal storage system only works for arrays that are regular, meaning that all of the rows have the same length and where all of the elements are machine numbers of the same type. Otherwise, the system automatically converts the array to a general expression. For example, this input replaces one of the elements in that array of inexact machine numbers with an exact integer rather than with another inexact machine number, so the elements in the new array are no longer all of the same type, and byte count shows that the result uses quite a bit more memory, which is the memory needed to store this array as a general expression. Results that can be stored in a more optimal form, however, are normally stored that way automatically. For example, matrix inverse applied to that last array gives a result that again uses 8 bytes of memory per element. In the Wolfram documentation, arrays that are stored in this optimized way are called packed arrays. There are various low-level functions for working more directly with packed arrays, such as the packed array queue function in the developer utilities package that returns true if the argument is a packed array. Since packed arrays are used automatically, however, it isn't usually necessary to use packed array queue or other special packed array functions. The packed array optimization will normally be used in any program that consistently works with regular arrays of machine numbers. In the Wolfram documentation, the guide page on matrices in linear algebra has links to information on features of the Wolfram language that are useful in linear algebra, including basic operations like matrix addition and matrix dot product, and a comprehensive collection of functions for matrix operations like inverse and singular value decomposition, and all of the other operations that came up in the examples.